My name is Shahriar, and I'm here to present our paper on behalf of my colleagues Martin Tamke, Cameron Nielsen, and Mette Thomsen. Our paper is called Durable Data Models for Circular Building Practices in Bio-Based Construction, the History Stack. For those of you who don't know about CITA, CITA is a Center for Computation in Architecture, and what we do is actually a little bit of IT, computational design, and digital fabrication. So you can see here some of the samples of our work. And this is part of a 5-year EU-funded project called Eco-Metabolistic Architecture, which is led by Mette Thomsen. You must all be, or maybe many of you may be familiar with the butterfly diagram developed by MacArthur Foundation, in which buildings don't experience single life arc from design to demolition, but rather multiple successive and even parallel life cycles and cascades as part of the building come into disrepair and are refit, repaired, reused, recycled, or replaced. Based in this context, in this circular paradigm, the need arises for a unified source of data about a given built entity in order to inform repairs and renovations, energy performance assessment, or life cycle analysis, and also simply general understanding of the entity's material behavior, where a circular paradigm necessitates a much more dynamic model that can adopt throughout a built entity's life cycles. Some efforts have been put forth to address this need, notably several projects funded through the European Commission since 2020. Each has their own shortcomings. Renovation or material passports tend to be static and monolithic, with great effort going into their establishment during the design phase and then laying dormant until needed. The relatively newer logbooks are continually added throughout a building's lifetime, but for example, IB Road log focuses on single-family residences. Aldren build log covers office buildings and hotels, and Extendo is oriented towards energy performance certificates. Oops, not going to the next one. To give an example from CITA's own research of the kind of use we might have for such a framework within a circular paradigm, Roland was a timber demonstrator structure which was later disassembled so that its component could be reused in a second structure. But when we disassembled the parts, we could see that with the photogrammetry there was a difference between the designed model and the 3D scanned model. And then we did the analysis to show these differences. So we need a platform where we could show all of these different types of data and their interface and the fusion of the different types. So we came up with the need of a unified but extensible framework for architecture data, which requires aggregation, activation, and analysis. And it follows the built entity through its life cycle, as I said before. In the aggregation phase, we are just collecting data, which is very well known. For instance, in here we have some of the sense data from the different temperature or humidity and other types of sensors that we use in our projects. Then we have analysis, where we are, of course, as I said, we are focused on biomaterials. So we do the analysis based on those sense data and to show what happened to these biomaterials. And then taking action. When we see the biomaterial is decayed or destroyed, we take action to do the repair. Slightly rewarded, and considering also the implied intermediate steps in this hierarchy, we arrive at 5 characteristics of the history stack: data, semantics, analysis, triggers, and actions. The name itself refers to the underlying time series nature of the data structure and the aggregation of stacking of many successive layers of data over time. As you can see, the different layers here. But we came up with 3 semantic links between all of the data that we have, which refers to the very core of the models. The time. We can compare the data based on the timestamp that we have, or the timestamp of the data collected. Object, looking at different types of the object, like point clouds, meshes, or B-reps, or all the different types of information that we have. And then the position, the registration, or the way the model was saved in a specific coordination system. And using these three semantic links, we were able to analyze our data and produce action. So what you see here is one of our tracking systems using computer vision and sense data coming together to lead to a certain action of repair for biomaterials. And of course, this is one of the projects of one of the PhD students that they actually repaired the biomaterials with additive manufacturing. Go forward faster. And as I showed before, this is the repair taking place. But we understood that it's better to save more data and filter later so that we can interpolate between the different types of data that we had. For instance, in this case, which is a 3D scan of the biomaterials. But as usual, the 3D scan usually takes only the surface, but not the other side of the panel, for instance. But what we were able to do was to create this semantic link and then apply the same change or deformation that happened to the 3D scan to the 3D model. With the feature-based, of course, tracking. In our latest project, which is a demonstrator taking place in the Danish Design Museum in Copenhagen, we again tried to practice this on an online platform. So we had all these different types of data, the design model, the manufacturing model, which is the 3D printing toolpaths, robot toolpaths, and then the assembly or as-built model, as well as the computer vision analysis, 3D scan analysis, and the inspection, which was done by humans, just someone going out there and taking notes on what they could see, because the 3D scan and camera cannot see all the details, but there are some small details that requires human inspection. And creating Excel sheets and repair models. All of this is actually demonstrated in a web platform that we created, and we have all this data collected and saved in the online platform. And then we create different fusions between them. So what you see here is actually at the ground truth of the data. And then we have a slider which we can go through these different timestamps. And maybe to this next slide, you can see the sense data, we can see the 3D scans, and then comparing all of this, like the 3D scans or the weathered model to the printing model and the design model. And to conclude, I have to say that so what we were aiming at was to create these links between the different models and maybe more fundamental research to see, because of course we didn't have any BIM models, but we think that BIM, MP, and the DBL take compartmental or monolithic approaches, but the history stack aims to balance on practicality and interoperability to ensure a long-term sustainability of the data. And thank you for listening.